Hello everyone. In this video, I'm going to present our recent work. It's about demonstration of a Hamiltonian-based quantum router using IBM Quantum Experience platform. So here you can see in the screen in the right side the picture of a router. You know, when you talk about classical communication network, then router is an essential component, right? So when we define a router, it's a device that carries data packets in a network system, you know, by receiving, analyzing, and forwarding them. So in the screen, you can also see this below the picture where, for example, we have an internet connection and we have different devices. We want that this data signals from internet, they should go to different devices, you know, without being lost in the network. So what does this router does there? It just connects your different devices and provides them the internet connection. You know, we have this complex communication patterns in this network. You know, it is being enabled by a router as it sends signals to various destinations according to the address information. So this router, it synchronizes a target internet protocol, which is also called an IP address of a given data packet, and chooses the most suitable way for it to reach its final destination, and then it transfers it accordingly. And when we say classically, you know, classical routing devices, they forward data packets between them to establish connections, right? So it is possible to exchange data packets between devices or to send data packets to the internet from devices. You see there, this each device on a network uh, receives an IP address from the router. You can see this router in between. You know, it sends the IP address to different devices. What happens with that? As a result, this data packets, you know, they travel to their intended destinations instead of being lost in the network. For data to reach the right device, we need routers to connect many devices within the network. Now we see this, the number of internet users, it keeps increasing day by day. The entries in forwarding tables have increased, making longest prefix matching operations more challenging. You know, if you are interested in learning about this classical routing system, how it works, there's plenty of literature available. You can have it. You can have a look on that to understand what does this mean, prefix matching. I will not go into that right now. So there are certain problems with the classical routing. You know, on classical networks, quantum information can be distributed, which is why quantum networks, you know, they enable functions that can't be addressed on classical networks. And this problem, you know, this number of internet users that keeps increasing day by day, it has been addressed in several studies and research that have improved the routing performance actually. Now we have this concept of quantum router, you know, using the quantum principles from the quantum mechanics, like entanglement, superposition. It holds a promise of improving our current technology. So in that sense, we have this quantum router uh, as a quantum analog to classical router. So it's a device that is proposed to direct quantum information, um, uh, quantum data signal in a quantum network system. So the novelty and contribution in this paper is that we implemented the blueprint of a quantum router on a 4-qubit system using IBM's quantum experience platform, which is available via cloud computing. And we verified the working of a quantum router based on system Hamiltonian by implementing a few conditions which have been proposed earlier in a paper um, whose link we will provide in the description if you are interested. That paper is our reference. We have implemented their theoretical conditions which they have proposed in their paper, in which they have proposed that this the information can be transmitted from the input qubit to the desired output qubit. What does that mean? That will be clear in the next slides. So when you talk about the methodology, you can see there in this in the picture we have this 4 qubits. Actually, we have this 4 qubit system here. Number one is input qubit, and we have 2 output qubits, and we have also a control qubit. As the name suggests, this control qubit, it controls the direction of transfer of the message, the data signal from input qubit to either output qubit 1 or output qubit 2. Now that will be determined by the state of control qubit. And also you can see this the coupling jx coupling, jz coupling. So this jx and jz, these are called transverse and longitudinal couplings, respectively. Jx is transverse coupling and jz is longitudinal coupling. Now this jx, it couples the input qubit with the output qubit first, and also it couples the input qubit with the second output qubit. Similarly, this longitudinal coupling jz, it couples the output qubits with the control qubit, right? Now, as the name suggests, as I talked about, the control qubit, it controls the direction of transfer of input message to the desired output qubit. This is what we do in here. So we have this control qubit. It can be either in 0 state or 1 state. Only 2 states are possible here, right? Also, the third state, that is the superposition state. So let's talk about first, it is in a 0 state. When it is in 0 state, the message, the input signal from the input qubit, it will get transferred to the first output qubit. Okay, now when this control qubit is in the 1 state, this input qubit, the input message from the input qubit will get transferred to the second output qubit. This is the whole idea of this quantum router here we are discussing. So this is actually the scheme which has been proposed by which has been proposed already in a paper. I talked about the reference paper we have. So this is the idea of this Hamiltonian, of this router. Now we have actually a Hamiltonian, it's Hamiltonian based, right? So we have different terms in here. You can see this delta 1, delta 2, these are the constants. Sigma 1, sigma 2, sigma 3, these are actually the Pauli matrices. And we have also JZ, JX. These are the couplings I talked about in the previous slide. And you can see we designed a circuit on the IBM's quantum platform. And in the third term, you can see this JZ coupling, JZ interaction between the control qubit and the first output qubit and the second output qubit. Remember this subscript 1 and 2 here. It represents the first output qubit and the second output qubit, and the subscript C represents the control qubit, and subscript I, it represents the input qubit, right? So you can see also in the circuit the coupling between the control qubit and the first output qubit and the second output qubit, then the coupling between the input qubit and first output qubit and the second output qubit. So this is the Hamiltonian that we are interested in here. Basically, we set a matrix representation for each term. We utilize the different quantum gates we have, available to express the matrix terms. Then the router of interest, the consists of 4 qubits. Actually, I talked about in the previous slide. At corresponding gates with appropriate parameters are fixed in the 4 qubit lines, right? So The conditions which we have followed here, I was talking about, these are the conditions here. Delta 1 equal to minus delta 2, 4 times jz by jx should be greater or equal to 1. Lambda, this delta should be equal to 2 times gz. Basically, when we follow these conditions, when we exactly follow these conditions such that we set this detuning as delta 1 equal to minus delta 2, only then we can observe that when the fourth qubit is in the zero state, the first output qubit and the input qubit are resonant. I was talking about in the previous slides here. I mean, when we have this control qubit, following those conditions, then this when control qubit is in the zero state, there will be coupling between the input qubit and the first output qubit. Message will get transferred between them. And when this is in one state, here you can see, and this message will get transferred to the second output qubit from the input qubit. So this will happen by following these conditions. And in this table, you can see by only following certain conditions, certain parameters for this JZ, like 4.78, 7.89, only at these values, the message will get transferred to either the first output qubit or the second output qubit successfully. I mean, with 98% of probability. For example, we have here 4.78. If we fix 4.8, for example, 80, then the message will not get transferred. We have observed it, right? So then the delta will take the value as delta equal to 2 times gz. Simply we have to multiply it by 2. These values we have to fix. These are the parameters we have to choose so that the message will get successfully transferred. And these are actually the results we got. First two figures, the above one, these are for output qubit 1. When the control qubit is in the zero state, the message from the input qubit will get transferred to the first output qubit. That's why I have written here on Q1, on Q1. So these two figures are for first output qubit. You see this probability of this message getting transferred from the first, from the input qubit to the first output qubit. You see this 1, 0 here. Okay, this is the control qubit, this is the second output qubit, and this 1 here, it is the first output qubit. The message got transferred to it with the probability of 0.98. Similarly, on value of 7.89, we get a probability 0.99. And now when we set the control qubit to the 1 state, we get the probability of 0.98, 0.99 on the second output qubit. So this is, it's very interesting result. I mean, the probability is above 0.98. I mean, 98%. That's a very good result. Now, after determining this these results, we also calculated the quantum state tomography. Based on measurements of the state of a quantum system, quantum state tomography, it determines the state of the system. It's a technique, or rather a standard technique, to verify and benchmark quantum devices. It has been followed in different researches, in different works. Here we present both experimental and theoretical density matrices of a quantum state. And upon comparing both of them, we can test the implementation of the quantum router. So you can see first we calculate the theoretical density matrix by following this formula, and then we will calculate the experimental density matrix by following this formula, right? By measuring in X basis, Y basis, Z basis, and calculating the probability of P of 0 minus P of 1. And that's how we do the quantum state tomography. After calculating both the matrices, density matrices, then we will calculate the fidelity. Why we calculate the fidelity? It is just to compare both of the results so that we will see the accuracy in our results. So you see this in the formula of this fidelity. there are both the theoretical density matrix and experimental density matrix. When we put the values of those in this formula, then we calculate the fidelity for different values for different parameters, that we talk about. We will get the fidelity, we will get the accuracy, right? Okay, so this is the accuracy we got. For first table it is for output qubit 1, and the second table is for the second output qubit. On these values, on these specific values of JZ 4.78, 7.89, and corresponding values of delta 1, 9.56, 15.78. Delta 1, it is for the first output qubit, and here this I mean, the working of this router, it depends upon JZ and delta 1, not delta 2 in the second output qubit. It will depend upon delta 2 in that case, right? In the second table I'm talking about. You see the fidelity here, the accuracy here, it is 0.99, it's 0.98. I mean, in every case, it is 0.98 or 0.99. We can say that the accuracy is almost, greater than 0.98 in both the cases, and that's really a good result. So this is actually these histograms, they represent the behavior of fidelity. We also were interested in exploring the behavior of fidelity with respect to different parameters that are involved in the Hamiltonian, like JZ, JX, delta 1, delta 2. So these four histograms, they just simply represent the behavior of fidelity. In the first diagram, we see the fidelity is almost 0.99 by changing the value of this JZ, 4.78, 7.89, and in every case, we have this 0.98 or 0.99 fidelity. And between those values, 4.78 and 7.89, the fidelity is below 50%. In some cases, it's 60%, 50%, 40%, but only at those specific values, we get the maximum fidelity. I guess we can also draw another plot here for those values also, where we can show the variation of fidelity that is below 50%. We can also have that plot. I missed that. So so these were the results in this paper. Now, as a future directions, if we want to do some further work in this direction, we can, generalize the scheme for n output qubit system. Then we have to modify the Hamiltonian also in that case for n output qubit system with the control qubits will be n minus 1. Right. For example, in our case, we have two output qubits. So the control qubit were n minus 1. That means 2 minus 1. We had one control qubit in our case, right? Now, when we have a general n output qubit system, the control qubits will be n minus 1, and the Hamiltonian will be like this that you can see on the screen. Simply, we have to add the terms. We have to include those couplings between different output qubits. When we have n times of output qubits, simply we have to add those terms in this. So this is the diagram for it. You can see this orange one, it represents the input message, and we have different output qubits that are being represented by green hexagons, and we have also n minus 1 blue hexagons, and they represent this what we call as control qubits, right? N minus 1, and then there are those parameters, these couplings, JX coupling, JZ couplings that we talk about. So what we got from this work, we demonstrated the working of quantum router based on the system Hamiltonian by following a particular condition. And when we summarize the result, it's that we verified that only at some specific values of JZ does information get transferred to the desired output qubit, and we verified that the control qubit, it is actually controlling the direction of transfer of the message from the input qubit to the desired output qubit. That's why it's called control qubit. It's very important result here. And also we performed a quantum state tomography, and we have verified our all results. And we have observed that the fidelity in each case is 0.98 or 0.99. I mean, it is above 0.98. And finally, we also presented the scheme for an output qubit system with a generalized Hamiltonian. So this is what we did in this paper. Thank you.